Welcome. This is the second question for AQA's AS Physics. This is the Unit 2, June 2009 paper. This is obviously question number 2. Now what I've tried to do, is again rather crudely, is draw what you're given in on the paper. Okay. So obviously we're told that there's this counterweight. It's on a lift, okay, there's the distance between the support and the point where the weight's being lifted up from the ship that's in the water is 32 metres, okay. We're told that the mass of this weight being lifted is 22,000 kilograms, okay. And there's a point which I didn't quite get to draw on my diagram, okay, because I didn't quite anticipate how long I was going to draw it for. Just at the top here of the crane, there's a point labelled P. But it isn't really that relevant in calculating your answers, okay? It says that when, for 2A, when the container is being raised, its centre of mass is a horizontal distance 32 metres, okay? So, as I said, it's shown on the diagram. Assume the tension in the cable for each of the 4 lifting cables is the same. Calculating the tension in the cable when when a container is lifted at constant velocity. Now, this requires knowledge of Newton's laws of motion. Sorry, I was trying to think off the top of my head. God, ooh, I've seen it. Yeah, sorry, Newton's first law of motion. I kept thinking it was his third. Sorry about that. So anyway, what I'm saying is, all the force is about, if it's at a constant velocity, it's not accelerating. So the force upwards is not greater than the force pulling it down. And obviously there's no forces acting on the side, so they must be equal. So in other words, for it to be accelerating at if it's moving at a constant velocity, there is no acceleration. In other words, the tension is equal to the weight. Okay, because the tension's pulling it up and the weight's trying to pull it down. And we know weight, obviously, is calculated by mg. So in other words, the tension equals mass times acceleration due to gravity. So T equals 22,000 kilograms times g. In other words, times 9.81. Okay, and that would be your tension. Okay, which I worked out to be 53,900 newtons, and that is your answer for part A. Part 1. Okay, so A part 1, 53,900 newtons. Okay. A part 2. Calculate the container's weight about point P on the quay side. It just means about point P. You know, you think, oh well, point Q is actually on the floor, whereas this isn't. It's at you know, you have to go up a little bit and then turn right and go along. Well, the principle stands that it's the force at a right angle, so it doesn't matter if this Q was 7,000 points down. Okay, it still has the same effect as if it's right there, right at the corner where the loading point is, okay? As long as it's 32 metres away perpendicular, it doesn't matter how far up or down it is, so don't get perplexed by that. It's as simple as it seems. So all you do is, the first thing I would do in this question is obviously state that, well, it's not worth that many marks really. First thing I would state is that moment is force times distance, okay? In other words, m equals F times d. You can tell it's perpendicular distance, okay? So obviously the moment, therefore, the force, as we know, is equal to the weight because the weight is a force as it is a vector. Okay, so the force is 53,900 newtons, or exactly, I think that might have been a little bit rounded actually. Not 100% sure, I can't quite remember. But anyway, it's 53,000 newtons, or what have you got for A part 1, times the distance, which is 32 metres. Okay, and that is your moment. Okay, so this is again just a case of putting this into your calculator Okay, so if you were to do that, you should get 6.9 times 10 to the 6 Newton meters. We have to state an appropriate unit. Now, I've mentioned this in my previous, I think one of my previous past papers. I think it was actually question 1 of this paper. But to work out, if you don't know the units, okay, in terms of, you know, obviously energy is in joules, but if you don't know the units, okay, for moment, okay, well, you know the units for force, which is newtons, and the units for meter, distance, which is meters. So you time it, what we're essentially doing is times x newtons by a certain amount of meters. In other words, it's newtons times meters. So you put the two words together, newton meter. Okay, so that's how you come up with units. But as I said, hopefully that's fairly self-explanatory, and that's a lot easier to explain how to combine the units rather than using that in question 1, which is a little bit more tricky. Okay, but the principle stands. Alright, so 2A part 3. It's a writing question, this one. Describe and explain one feature of the crane that prevents it from toppling over when it is lifting a container. Okay, so we have to look at this. Well, we've just been, you have to think, well, if this question strikes you as what the hell do I do for this part, you think, well, what is on this crane? Well, quite clearly, structure's not going to be doing anything. All the structure's there to do is to physically hold it up. It's not there to balance anything, okay? And you have to get into your mindset, we've just been answering a part of a question on moments, so it must be something to do with moments. And the thing that it mentions about prevent it from toppling, well, that is quite clearly to do with moments. So definitely this question will have something to do with moments. So we have to pick one feature of this crane and explain why it stops it toppling over. Okay, so therefore we've just talked about moments, and this thing, whatever it is, must be to do with moments. And if you can look quite clearly on the diagram, there's a counterweight there. Now, this has put more emphasis on the fact that it's going to be something to do with a counterweight, because if you look at the rest of the questions, the next two little parts, okay, are simply to do with Young's modulus and tensile stress, which is quite clearly nothing to do with this counterweight. Now, you wouldn't have put it on there for no reason, okay, especially mentioned it and put it where it is. So it must be something to do with the counterweight and something to do with moments. Well, prevent it toppling over, well, that implies therefore it's going to remain in equilibrium. And for an object to remain in equilibrium, the statement to do with that, in terms of the moments, okay, is that the moments must remain in, the sum of the anti-clockwise moments must equal the sum of the clockwise moments for the object to remain in equilibrium. Okay, so therefore, well, if you think, well, what has this counterweight got to do with moments? Well, if we pick that Q as the centre, okay, just an example, point the pivot, there's a counterweight providing an anti-clockwise direct moment, and there's the obviously the weight, which is of this mass, which is providing the clockwise moment. Okay, so the answer you would put for that, obviously it's 2 marks, so you've got to pick one feature of the crane and explain how it prevents it from toppling. So for the first mark, you would pick the fact that there's a counterweight to stop the crane toppling over, and the second mark was for saying the reason for this, or however you want to explain that, probably sound a little bit less of a complete and utter tosser. The counterweight provides a anti-clockwise moment, okay, to balance the clockwise moment of the weight, the masses which are being lifted off the ships. Okay, so that would be your 2 marks there. All right. The next part of the question again it requires us to do a bit more calculation. Okay, it says each cable has a cross-sectional area of 3.8 times 10 to the minus 4 meters squared. So I would underline that, and it tells you that, but it's always nice to just know what you've got, because with these questions that aren't quite obvious, well, this one is, but any calculation question I always mention and note down what you know. I don't know how you can quite get through physics and get your questions right without doing that. You must be pretty smart. Okay, so it's 3.8 times 10 to the 4 meters squared, and that is the area. or the cross-sectional area of one of these ropes. Okay, so these little green things are meant to represent the ropes. Okay, there's a diagram, but I've just kind of drawn it cruelly on there. Calculate the tensile stress in each cable, stating an appropriate unit. Now, even if you didn't know, well, I said the formula for tensile stress is on the formula sheet, but if you can be bothered to look at that, well, quite clearly, we've got an area here and we've just been asked to work out tensile stress. And one of them is to do with delta L over L, and one of them is to do with tension over area. Okay? So, quite clearly, we've just been told area, so it's going to be the tension over area. In other words, okay, so we know that there's tensile stress. So my first little thing I'd write down is tensile stress is equal to force over area. Now, it's asked us to work the tensile stress in each cable. Oh, damn it. For part AI, sorry, I do apologise. I got this wrong. That equation which I wrote down, I think it was 22,000 times 9.81. Sorry, I should have divided that by 4 because it asked for the tension in each cable. Now the answer was right, I just forgot to add the divide by 4 thing. So even the best of us get it wrong at times. So I do apologise. And the reason for this is obvious because it just made me think of this part. So in the first part, what I should have told you that I was calculating, should have shown that we were working out the tension in each cable. Okay. So therefore, if it wants the tensile stress in each cable, now we have to use the force which is associated with each cable and the cross-sectional area which is associated with each cable. Now we're told the cross-sectional area of one cable is 3.8 times 10 to the minus 4, okay, which is fair enough. But what's the force associated with each cable? Well, the only force is the tension, okay? Or, as I said, that's equal to the weight of the object. So, as I said, you know, the tension or the weight is the same thing because tension equals weight if it's in a constant velocity. So you can think of it as either. I think of it as a tension, okay? So the tension, because the tension is a force, we can put that as the force. So you can make that equal tension over area, okay? So you sub in your 53,900 or whatever you got for 2A part 1 over the area, which it's told you is 3.8 times 10 to the minus 4 meters squared, okay? And therefore that would give you an answer of 1.4 times 10 to the 8 newtons per meter squared. Again, it tells you to state an appropriate unit. So you should be able, as I said, the principle of calculating your own units is very, very key in Unit 2. Okay, now what we've got here is newtons over metre squared. Now whenever you would have something like 1 over x, obviously whatever you have on the bottom has a power of minus 1, or if it's squared it has a power of minus 2, okay, because you take away the powers. Okay, so basically you're doing newtons over metre squared. In other words, you're doing newtons and then you're taking away the power of 2m, okay, because it's m squared, okay. So if that was x squared, it'd be 1 over x squared, it'd be x to the minus 2, so therefore it's m to the minus 2, in other words, newtons per metre squared, okay, and that's your units. So hopefully, as I said, that was really just an association question, but I mean, there's no other force or tension that you could have used. Now, the key mistake with this, okay, is using the wrong answer, okay. So, however, with AQA, obviously not going to penalise you more than once. Now, if you did spot that it was asking for each cable, okay, and you put the tension in each cable because you thought that was just the weight was the weight of each cable or whatever. So you did 22,000 times 9.81, but you put that answer for the first part of A part 1, okay, and you said, well that's the tension in each cable, and you use that answer for the tension over area and put that as the tension in each cable is some ridiculously huge number. Now, hopefully that should have struck you in the exam as, well, that's ridiculously big for tensile stress, and you bear in mind that that stress over strain is the Young's modulus, okay? which is what we're going to come on to next, and that would have hindered your second part of this as well. But basically, they will only penalise you once for a mistake. So, as I said, if you use the tension for the whole thing as the tension for each cable, and you put that into your answer for 2 part B, you wouldn't be penalised again for that. You could still get all the marks for 2B part 1, but you get the wrong answer. So hopefully, as I said, that kind of made a little bit of sense. Alright, so 2B part 2 is a little bit more challenging. It kind of asks you to manipulate the Young's modulus equation, and I think it's quite a nasty one, this, purely because it doesn't give you all in SI units, which is a common case with Unit 2 questions, okay, mechanics. They like to, not all the time, but some of the time, they don't like to put it in all in the same SI units, in terms of the, such as in this question, we're told that just before the continuum figure 2 was raised, the length of each cable was 25 metres, so the first thing you write down was the initial length, or I just leave it as length is equal to 25 metres. Show that the cable extended by 17 millimetres when it was raised from the ship. Okay, so we've got to show that delta L is 17 millimetres, okay? And obviously, when we work out the Young's modulus equation, we work out delta L. Well, it gives it us in metres, so we need to convert that to millimetres, okay? But anyway, we don't know delta L, we have to prove that. So that's kind of the first little bit of the question that you might get thingy with. And it tells us that the Young's modulus of steel is, so it's labelled by E, as 2.1 times 10 to the 11 pascals. Okay, so that's the Young's modulus of steel. Now you should be aware, okay, it doesn't give you it in the a formula sheet directly, Young's modulus. It gives you it as tensile stress over strain, okay, but it gives you the formula for tensile stress, which is obviously tension over area, and it gives you the formula for tensile strain. So if the formula doesn't come to you straight away, you might want to do a little bit of working out, and I will do that for you. Okay, so we know that Young's modulus is tensile stress over tensile strain, so in other words, the tension over area divided by delta L over L. Now you quite clearly flip the fraction and times it, so the Young's modulus is TL over A delta L. Okay, so in other words, now it's up to you how you go about answering this question. Now quite clearly, it's just a rearrangement of that question because you've got all the other bits of the question that you need, okay? Now quite clearly you should know, because we're working out the tension, because that's the cross-section, we know the, obviously we're not given everything in this question, we use the information we've already worked out. Okay, so you can use this formula that's together, or you can use the one that's split up, because you know what the tension over area is. We've just worked it out in the previous part 2b part 1. So you could do Young's modulus is equal to, because we said that was 2.1 times 10 to the 11 pascals, is equal to tension over area, which is tensile stress, which we've just worked out was 1.4 times 10 to the 8. Now to be more specific, okay, I would just use your answer, directly hit the answer button from, because you've just done 2b part 1, that's likely to be the answer, which is now stored in your calculator's memory. Okay, so just leave that as your answer point, so you don't have to type it out again, which obviously increases your accuracy. And we divide that, okay, by delta L over L. Now we know L is 25 metres, so we just sub in 25 metres there. And it's really just a case now of rearranging this equation to get delta L, okay? And as I said, you could just, swap these two around by dividing by delta L over 25, okay? Or actually flipping that fraction, so it's 25 metres times 1.4 times 10 to the 8 over, So it's just a case of rearranging that equation, okay, and getting delta L. Or you could sub in your values for E equals T times L over A times delta L, okay. You should be aware, obviously, that tension in each cable is this 53,900 newtons. You should be aware that the area, cross-sectional area, well, it's told you at the start of 2B, which I think was 3.8 times 10 to the minus 4 meters squared. Okay, you should know that as the area. And just sub it all into, and obviously the length is 25 meters, E is 2.1 times 10 to 11 pascals. Put that in the Young's modulus equation and simply rearrange, okay? But the key thing with that is if you do, obviously either method you use, you will get an answer which is in meters, and you need to be able to convert that to millimeters, okay? And obviously you just times it by 10 to the 3. Yeah, you just times it by 10 to the 3. Okay, so you get an answer of 0.0168 meters, okay, which is obviously the same as 17 millimeters. Okay, so hopefully that made some kind of sense. I know I didn't really do the calculation at the end, well, simply couldn't be bothered. But as I said, hopefully, it's just really a case of rearranging the equation and nothing more than that. Okay, so thanks for watching. Hopefully, not budge too much, and it's been kind of bearable. We'll see you in the next video. Thanks for watching.